So we're going to move to the Indian River case study. As John had mentioned, it is our flagship as far as bridges. We installed the system from its conception and its design, how the conduits were ran, and to also ensure the safety of the people who are working on the bridge. So as they would pour each section, we would embed sensors in the concrete, and I'll show you how we did that. And like I said earlier, later on, it was decided for the Homeland Security System to be installed, that the DoD had funded in the Federal Highway Authorities. So we didn't have to change anything in the infrastructure. All we had to do was add the additional optical sensors to produce a very nice security system. Now, one of the major events that did happen on Indian River was Hurricane Sandy. Hurricane Sandy, as you can tell, took out the approaches to the bridge, as well as this was some access roads that ran alongside the bridge. But it took out the beach, the dunes, which is normally way hundreds of feet further back toward the water. So it took them many weeks to actually rebuild the approaches to that bridge. But what they were very impressed with was during that hurricane, within 8 hours, we were able to determine that there was no structural damage to that bridge. Now, you have to still do the visual inspection and so forth, but there was no key elements that was affected in any way. So this is some videos that I captured during that hurricane, and you can see the stay cables and how they were disrupted with some of the winds. That was the main thing that we saw. The main strain and stresses was applied to the stay cables themselves. These have a plus or minus 2G reference, but at times, this was at the beginning of the hurricane, and at times these were peaked at a 2G and above during that storm. So we were able to watch how the pylons reacted and how they moved, and also all of the decks and how they reacted, in addition to understanding the frequencies that was applied to the supports themselves. So there was a lot of value. There were some articles written that highlighted this particular system after the storm had passed. Like I was showing you with the models earlier, we always create a map and where the sensors are located, whether they're embedded or surface mounted, and so forth, to get a client approval. We also, as I had mentioned earlier, and you saw in the video of the IntelliOptic software, from the model, we actually built these zones so that when you went through the software into these various zones, you were looking at data specific to those areas. And then also the same model, it takes about 3 days to create usually, even the most complex models, because we don't do all the detail, just the dimensional data, the links, and then the general shape matches the design itself. So we use this also for our installation purposes, not just the software. Of course, in the very beginning, the pylons was the first thing that we had to install the optical sensors in, mounted to the rebars. You had to come up with a lot of methods. This was the very first optical system. No one had ever done it before. We created a lot of very special applications and ways to run the cabling in the concrete and not damage the fiber. So on the pylons, for instance, before the forms were put into place, we would go back, place the sensors, run the optical cable, but we had to have a way to exit out of those pylons after the concrete cure. So simply, we just took a PCV pipe, placed wood on the inside with a rubber cap, with optical inlets, seals to the interior of the PVC pipe. So when the forms were put on the inside here, we would screw into this wood piece and it would hold it in place. And then when the forms were removed, of course, the screw was pulled out and the forms removed. In turn, once the curing process had taken place, then there's holes that are in the concrete at the different tier levels. And so we just cut the rubber on the end and pull the fiber out, and of course array from one level to the other, all the way to the top for accelerometers, tilts, all the optical security systems that were placed in for the pylon entryways and also the hatch doors. We also developed a method in which to run in the deck. The next slide shows the deck in its entirety. But wanted to show you what we came up with 14 locations across the entire deck. Now these are very close together for the purposes of representing what we did. But we had embedded corrosion sensors, both optical corrosion and analog corrosion sensors, step sensors. We embedded the optical sensor here that I was showing you earlier with both temperature and strain built within the same tube. Now the reason we use this type of design was that it's made of Teflon, and Teflon does not stick to the concrete, so you don't damage the body in any way once the concrete is cured. And then also wherever we exited from that deck, then we had deck plates in 14 dual locations. When I say 14 locations, there were two, one across from each other. We placed tilt sensors, accelerometers, and then also arrayed between, there might be 40, 50 feet in between each one of these boxes. We did not run PVC conduit throughout the deck. It was just at the entryways. The cable was made special so that it can be placed directly into the concrete. So in the picture on the previous slide, then these are the locations that those boxes were placed with the embedded sensors, and where we would come to the surface to do our attachments in these boxes. Same thing with the pylons. There was a transfer made from the pylon body itself over to the deck with a flexible conduit. And we had displacement sensors for movement around the deck to monitor the movement around the deck and the pylons themselves, as well as the expansion joints and, of course, the stay cables. This is where we were making our final connections to the accelerometers on the stay cable. The stay cable was covered with a composite cover and filled with gel, and the accelerometers were mounted on the outside of the composite pieces. There were spirals the entire length of the stay cable to allow water runoff. So these spirals that went down the entire length, we had to be careful about how we designed this so there was no interference with the water runoff. So we did make those final connections from the stay cables themselves to the boxes, as you see being done here, and while we're also installing up top here from the cable down to these boxes. Of course, we use iPads so that every connection that's made, we can connect directly to the master control panel and understand, without anyone being at this location, which is remote, being able to see that everything is active. These are the displacements I had shown you earlier on the different types of sensors we were using. and I'm showing this in the picture where there's an expansion joint that we were monitoring at each end of the bridge and also around the pylons. Because it's such a corrosive environment, we built special covers to go over and seal off the ends to not allow any kind of rust. Even though we use high-grade stainless steel, the corrosive environment and weather can have a great effect on different types of sensors. And there again, that's the value of the optics. They're not affected by high corrosive environments. And this is where we're exiting now through a PVC that's filled with a gel so that no moisture can be allowed inside the concrete once everything has been placed. The security system. We were well into this project, about a year into the project, and then they made the request that we need a homeland security system on this structure. So we placed various cameras, and you see here under the deck they had infrared that was used on them. They had long range so they could see at night. And then, of course, the capability of 36x zoom for anything that may happen underneath the bridge. Now, these platforms, at each pylon, we put optical sensors. And these are very, very sensitive and very accurate. If anyone steps on these, on the platforms, then these cameras would train on those locations. Also, with the optical switches I was showing you earlier, if you open this door, then the cameras would train on that location. Same thing for the hatch doors, that we put cameras on the pylons. They were used for multiple purposes, not just for security, but for accidents or things that may occur on the bridge. They were used for that purpose as well in the command and control center. But these cameras were smart, and they responded directly to the sensors that were being activated. Further on the security, this is the optical switch I was showing you earlier, but we used that optical switch on the communications hut that was underneath the bridge. This communications hutch was used to also place local telecommunications in that area, as well as our equipment, which is shown here, and a power backup generator, diesel generator that was behind the house, and UPS systems on the inside. But also in that house, the navigational lights on the bridge and the lighting on the cables and the aerial lights were all controlled from this location. About half of that was actually incorporated into our system since we already had the PCs in place. We placed a lot of the UPS software, and also the generator, we could tell them whether it was operational or not as an additional backup. Earlier I had shown you this platform. It's an entryway into this hub house, and then we placed cameras there as well. And this camera would begin recording just like the other cameras we placed up on tops of the pylons as well as underneath the deck. Should anyone enter the hub house, then it would begin a recording process. Now there was work orders tab that was put into the system to where if there was somebody supposed to be on site and it was scheduled, then they would call in and check, and then to prevent false warnings. This is a view of the control panel that we had. One system on this side was for security. One system here was for the structural health monitoring system. And same thing with the interrogator. We had one interrogator for structural health and then one for security. They wanted a redundant system so that if this PC crashed or this workstation crashed, the other one would take over its job. So we use smart IP addressable switches for all the cameras, for the interrogators to switch from one PC to the other if needed. This happened once in the last 7 years to where there was a hard drive failure, and this system here had to take over the work of this one. There's also RAID drive backups, and of course sharing of monitors and keyboards and mouses. The information from this location was transmitted to the command and control center, the traffic management center for Deldi. Now, one of the final steps that we took for before the bridge was open was doing a load test. So I'm going to run a video and let you listen to this. It's a short clip of what we did to come up with a baseline for all of the information that was gathered.